Right now, the device in your pocket knows exactly where you are. Not roughly, not the city or the street. It knows your position on the surface of a spinning planet to within a few feet. Ask it, and the answer comes back in an instant. A blue dot, sitting precisely on top of you. It feels ordinary. It is one of the most extraordinary things human beings have ever built. Because to find that blue dot, your phone is doing something almost unbelievable. It is silently listening to a handful of clocks. Not clocks on the ground, clocks in space. More than 20,000 kilometers overhead, a fleet of satellites is circling the Earth, and each one carries an atomic clock so precise it would lose barely a second in millions of years. Those clocks are whispering the time, constantly down to the entire planet. And from nothing but those faint signals from space, your phone works out where you are standing. No fee, no subscription. Free, for everyone on Earth, every second of every day. But this gift wasn't built for you. It was built as a weapon. And the story of how it got here runs through nuclear submarines, a downed airliner, and Albert Einstein himself. To understand why this is a miracle, you have to remember how hard the question used to be. For almost all of human history, the simple question, "Where am I?" had no good answer. On land, you used landmarks. At sea, you were nearly blind. Sailors could find their latitude, how far north or south they were, by measuring the sun. But longitude, how far east or west, defeated them for centuries. Ships missed entire islands. Fleets ran aground on coastlines their captains thought were hundreds of miles away. Whole crews starved, lost on an open ocean, because no one could say exactly where the ship was. Knowing your position was quite literally a matter of life and death. And by the middle of the 20th century, it had become a matter of military power. A bomber needed to know where it was to hit a target. A submarine carrying nuclear missiles needed its own position perfectly, because a mistake of even a mile meant the missile would miss. The most powerful militaries on Earth were spending fortunes on a question children now answer with a tap. If you find these hidden engineering stories as fascinating as we do, take a second to subscribe. We tell the real story behind the world's greatest builds. And the answer, when it finally came, arrived from the strangest possible place. A small metal sphere, beeping as it crossed the night sky. In October 1957, the Soviet Union launched Sputnik, the first artificial satellite, and the world looked up in shock. At a research laboratory in the United States, two young physicists, William Geer and George Weifenbach, did something simple. They tuned a receiver to the steady beep falling from the passing satellite, just out of curiosity, and they noticed something. As Sputnik approached, the pitch of its beep rose slightly. As it moved away, the pitch fell. It was the Doppler effect, the same reason a siren sounds higher coming toward you and lower going away. From that shifting tone alone, the two men realized they could calculate the satellite's entire orbit. They could tell exactly where it was in the sky, just by listening. Then their boss asked a question that changed everything. "If you can find the satellite's position from its signal," he said, "could you turn it around? If you already knew exactly where the satellite was, could a listener on the ground use that same signal to find their own position instead?" The answer was yes. And the United States Navy realized, almost immediately, what that meant. A satellite in the sky could tell a submarine hidden in the ocean below precisely where it was. The Navy had an urgent problem. Its new Polaris submarines carried nuclear missiles that could end a war, but only if they hit their targets. And to aim a missile, the submarine first had to know its own position. Exactly. Out in the deep ocean, with no landmarks, that was almost impossible. So the Navy built the world's first satellite navigation system. They called it Transit, a small group of satellites in low orbit, broadcasting steady signals down to Earth. A submarine would surface, listen to a passing satellite, measure the Doppler shift in its signal, and from that work out where it was floating. For the late 1950s, it was astonishing. For the first time in history, a machine in the sky could tell you your place on the planet. But transit was crude by today's standards. It could only give you a fix when a satellite happened to be passing overhead, which might be just once every hour or two. It worked best for something moving slowly, like a submarine, and barely at all for a fast-moving jet. It told you where you were, but only now and then. What the military really wanted was something far more ambitious. A system that could tell anyone, anywhere, moving at any speed exactly where they were, instantly, all the time. And the key to that turned out to have almost nothing to do with space, and everything to do with time. here is the secret at the heart of the whole system, and almost no one knows it. GPS is not really a map in the sky. It is a clock in the sky. The breakthrough came from a researcher named Roger Easton, who realized that the entire problem of position could be turned into a problem of time. Think about it this way. If you know exactly when a signal left a satellite and exactly when it reached you, then you know how long it traveled. And because that signal moves at the speed of light, a known fixed speed, the time it took tells you the distance it covered. Time becomes distance, but this only works if the timing is almost perfectly accurate. Light travels about 30 centimeters in a single billionth of a second. So if your clock is off by even a tiny fraction, your position is wildly wrong. Ordinary clocks could never be that precise. Atomic clocks could. An atomic clock keeps time by counting the unimaginably steady vibrations of atoms, ticking billions of times a second. And it stays accurate to within a billionth of a second. Easton's insight was simple and radical. Put atomic clocks into orbit and let them broadcast the time itself. By the early 1970s, two rival military programs were chasing versions of this idea, and they were about to be forced together. By 1973, the idea was scattered across the American military. The Navy had its timing satellites. The Air Force had its own competing navigation program. Each had pieces of the answer, and neither had all of it. And the Pentagon was tired of paying for both. So, the job of combining them fell to an Air Force colonel named Bradford Parkinson. Over the Labor Day weekend of 1973, while the Pentagon was nearly empty, Parkinson gathered a small team in a borrowed set of offices. For 3 days they argued, sketched and rebuilt the whole concept from the ground up. They took the best ideas from every program, the atomic clocks, the orbiting transmitters, the time-based ranging, and fused them into a single, coherent design. They called it NAVSTAR. The world would come to call it GPS, the Global Positioning System. The plan they drew up that weekend was remarkably close to the system still flying today. Satellites carrying atomic clocks, broadcasting their exact time and position. Receivers on the ground listening to several of them at once. And from those signals alone, anyone could calculate where they were, anywhere on Earth, at any moment. It was an elegant design. But that raises the real question, the one that makes the whole thing feel like magic. How exactly do a few signals from space tell a receiver where it is? Here is how it actually works. Every GPS satellite is constantly broadcasting two things: where it is and what time its atomic clock says it is. That's it. A tiny, repeating message. My position is here, and the exact time is now. Your phone catches that message, and because the signal traveled at the speed of light, your phone can compare the time stamped on the message with the time it actually arrived, and work out how long the signal took to reach you. Multiply that tiny delay by the speed of light, and you get a distance. Now you know one thing: you are exactly this far from that one satellite. But that isn't enough. Being a known distance from a single satellite could put you anywhere on a vast sphere around it. So your phone listens to a second satellite and gets a second distance. Two spheres overlap in a ring. Add a third satellite and a third distance, and those three spheres meet at essentially a single point, your location. This is called trilateration. 3 measurements of distance, from 3 known points in the sky, pinning you to one spot on the planet. It is the same trick a surveyor uses with 3 landmarks, except the landmarks are racing overhead at thousands of miles an hour. 3 satellites, 3 distances, 1 answer. Except there's a catch, and to solve it, you need a 4th. The catch is your own clock. Everything we just described depends on measuring time with incredible precision. The satellites can do that. They carry atomic clocks worth a fortune. But your phone doesn't. Your phone has a cheap quartz clock, the same kind in a basic wristwatch, and it is nowhere near accurate enough. Even being off by 1,000th of a second would throw your position off by hundreds of kilometers. So how does a phone with a sloppy clock manage to be accurate to a few feet? With a beautiful trick. It listens to a 4th satellite. With only 3 satellites, the math has 3 unknowns it can solve: your position east to west, north to south, and your altitude. But add a 4th satellite, and now there is enough information to solve for a 4th unknown as well: the error in your phone's own clock. The receiver essentially asks, what clock time would make all 4 of these signals agree perfectly? Whatever answer makes everything line up must be the true time. So your cheap phone, by listening to 4 atomic clocks at once, corrects itself into atomic clock precision. It is genuinely elegant. But there is one more problem with time in this system, and this one is far stranger. To make GPS work, engineers had to account for something most people think only matters to physicists: the fact that time itself is not constant. Albert Einstein proved, more than a century ago, that time flows at different rates depending on how fast you move and how strong gravity is. And the atomic clocks on GPS satellites feel both effects at once. First, the satellites are moving fast, about 14,000 kilometers an hour. Einstein's special relativity says that motion makes a moving clock tick slightly slower, so the satellite clocks fall behind. But the satellites are also far from Earth, 20,000 kilometers up, where gravity is weaker. Einstein's general relativity says that weaker gravity makes a clock tick slightly faster, so the satellite clocks also race ahead. The two effects don't cancel out. Added together, a GPS satellite's clock runs fast by about 38 microseconds every single day. That sounds far too small to matter. It absolutely does. Remember, light travels 30 centimeters in a single billionth of a second. So an error that tiny, left uncorrected, would push your position off by roughly 10 kilometers every single day. Within minutes, GPS would be useless. Maps would be worthless, so the engineers built Einstein's equations directly into the system, deliberately tuning the satellite clocks to run at the wrong speed on the ground, so they tick correctly in orbit. Every time you use GPS, you are proving relativity is real, and all of this depends on a small fleet of satellites arranged with great care. For the whole system to work, you need to be able to see at least 4 satellites from anywhere on Earth, at any time of day. That is a remarkable thing to guarantee on a spinning planet. The solution was a carefully designed constellation. The plan called for 24 satellites, working together, spread across 6 separate orbital paths circling the globe. Each satellite sits about 20,200 kilometers above the surface, far higher than the space station, but well below the distant satellites that hover over a fixed spot. At that altitude, each one loops all the way around the Earth roughly twice a day. The orbits are tilted and spaced so that their coverage overlaps everywhere, over cities, oceans, deserts, and poles alike. Stand anywhere on the planet, look up, and at least 4 of them are always above your horizon, even though you can't see them. Building this was a slow, expensive grind through the 1980s. Satellite after satellite was lifted into orbit, one launch at a time, gradually filling out the pattern. It would take years to complete. And while the constellation was still being built, a tragedy in the sky would suddenly change what this military system was for, and who would be allowed to use it. On the 1st of September 1983, a Korean Airlines passenger jet took off on a routine flight from Alaska towards Seoul. Somewhere over the North Pacific, the aircraft drifted off course. A small navigational error, compounding mile after mile, carried it slowly and silently into forbidden Soviet airspace at the height of the Cold War. The Soviet military, fearing a spy plane, scrambled fighters, and then they fired. The airliner was shot out of the sky. All 269 people on board were killed. The world was horrified. And the cause, at its root, was a navigation mistake, an aircraft that simply did not know precisely where it was. In Washington, President Ronald Reagan responded with a decision that would shape the modern world. The United States had a system, still being built, that could prevent exactly this kind of tragedy. So Reagan announced that GPS, once completed, would be made available to the entire world free of charge for civilian use. A military system, designed to guide weapons, would also become a gift to ordinary people. To airlines, to ships, to anyone who needed to know where they were. It was a stunning turn. But before GPS could become the quiet utility we know today, it would first have to prove itself somewhere far more brutal, on a battlefield. In 1991, the Gulf War gave GPS its first great test. The constellation was still incomplete, with only part of its satellites in orbit. But it was enough. The battlefield was the open Iraqi and Kuwaiti desert, a vast, featureless expanse of sand with no roads, no landmarks, nothing to navigate by. For centuries, armies had gotten hopelessly lost in terrain like this. Coalition forces used GPS to move across it with confidence, day or night, even in blinding sandstorms. The decisive maneuver of the war was a massive surprise flanking attack, swinging tens of thousands of troops far out into the empty desert to come at the enemy from the side. That maneuver was only possible because every unit knew exactly where it was, and exactly where it was going. There was just one problem. The military had so few GPS receivers ready that there weren't enough to go around. Soldiers and their families back home rushed to buy commercial units out of catalogs and ship them to the front. The system meant to be a closely guarded military secret was being supplemented by gear ordered from civilian stores. GPS had proven it worked. And yet, the version offered to the public was still being deliberately held back, made worse, on purpose. The military had a fear. If GPS was too accurate, an enemy could use it against them, to guide a missile, or strike a target with precision. So they built in a deliberate flaw. They called it selective availability. The satellites broadcast two kinds of signal: a sharp, precise one reserved for the military, and a second one for everyone else that was intentionally scrambled, its timing slightly corrupted. For civilians, this meant your position could be off by 100 meters or more, good enough to find a city, useless for finding a specific address. For years, the public got a deliberately blurred picture of where they were. Then, just after midnight on the 2nd of May, in the year 2000, that changed. President Bill Clinton ordered selective availability switched off. Around the world, in an instant, civilian GPS receivers suddenly snapped into focus. Accuracy leapt from the length of a football field down to just a few meters. Overnight, GPS went from a rough guide to a precise tool, and that single decision unleashed everything that followed: turn-by-turn car navigation, ride-hailing apps, food delivery, precision farming, a blue dot you could actually trust. The modern world of GPS was born at that moment. But keeping it accurate takes constant, invisible work. GPS feels like it just works, on its own, forever. It doesn't. It is tended constantly, by people you will never see. Deep in Colorado sits the Master Control Station, the brain of the entire system. Around the world, a network of ground antennas and monitor stations quietly watches every GPS satellite as it passes overhead, tracking each one with extraordinary care. Here is the problem they solve. Those atomic clocks in space, as precise as they are, still drift by tiny amounts. The satellites themselves wander ever so slightly from their intended paths, nudged by the pull of the moon, the sun, and the faint pressure of sunlight itself. Left alone, these tiny errors would slowly poison the accuracy of the whole system. So the ground stations measure exactly how far each satellite has drifted, and how far its clock has slipped. Then, every day, they beam corrections back up to the satellites, gentle adjustments that keep the clocks honest and the orbits known. It is endless, invisible maintenance, keeping a fleet of flying clocks in perfect agreement. And we lean on those clocks for far more than finding our way. We have quietly wired the entire modern world to depend on them. Most people think GPS is about location. Its deepest job is actually about time. Because every GPS satellite is broadcasting the exact time, the system has quietly become the world's master clock. And a startling amount of modern life is secretly synchronized to it. Power grids use GPS time to keep electricity flowing in perfect step across vast networks. Financial markets use it to timestamp trades to the millionth of a second. Cell phone towers rely on it to hand your call smoothly from one tower to the next. Banks, data centers, and the internet itself lean on those signals from space to stay in sync. We have woven GPS so deeply into civilization that, like the undersea cables carrying our data, we barely notice it is there. Which is exactly why it is dangerous to depend on. The signals reaching us from 20,000 kilometers away are astonishingly faint, easy to jam with a cheap device, and possible to spoof, feeding a receiver false information. A system this critical and this fragile is a tempting target. Other nations noticed too and built their own. Russia, Europe, and China each launched rival constellations of their own. The sky is now full of competing clocks, and yet it all traces back to one idea: a handful of clocks circling overhead. So think about that the next time a blue dot finds you on a map. It did not come from nowhere. It began as a Cold War weapon, a way to aim nuclear missiles from submarines hidden in the ocean. It was built by physicists who listened to a beeping Soviet satellite and asked a question no one had thought to ask. It runs on atomic clocks so precise they have to be corrected for Einstein's relativity, 20,000 kilometers above your head. It was open to the world because of a tragedy in the sky, and unlocked fully by the stroke of a pen one night in the year 2000. And today, every human being on Earth can use it, for free, at any moment, simply by looking up, even though we never do. A weapon meant to destroy targets became a quiet gift to all of humanity, handed out for nothing. There are clocks circling above you right now telling you exactly where you are. The greatest navigation system ever built was made from atoms, light, and the simple refusal to ever be lost again. If this changed how you see the device in your pocket, subscribe. There are more impossible builds waiting to be uncovered.